We're reaching the point in the semester where attendance drops enough that I can just start telling you the answers to the midterm questions.
Please do.
Is it a handout?
It would have to be, because otherwise it might show up online somewhere.
The majority of the questions come from the lectures since we've had it.
Yes, that's fair to say. Lecture and reading. I mean, there's some stuff from the readings that I haven't covered. But I really want to put a question about Canoma on the midterm, so expect that. Just because, then I can say that we did that. All right. How's everybody doing? We're in this like quasi feedback state today. It's not good. Whatever, good enough. What's going on? What's exciting? Contextual inquiry thing. That going okay? I totally forgot to put administrivia slides into this lecture, so at some point maybe we'll stop and talk about that. Oh well, we're going to start by introducing Carrot.
Introducing Carrot. Carrot uses an innovative combination of nutrients to provide a seamless experience for your digestive system. Here's how it works. Swipe with 2 fingers to feel the carrot's rough texture. Pinch carrot with your thumb and forefingers. Then make a lifting motion to lift carrot to your face. It's that easy to get fresh, quality nutrients delivered wirelessly to your body. Carrot works seamlessly with all your favorite apps. And Carrot is compatible with a wide variety of sauces and dips. And coming soon, integration with Beats by Dre. Carrot uses virtually no power, so you can take your carrot anywhere. When you find a carrot you love, it's easy to share with friends. When you're done with your carrot, swipe upward. Don't worry, your carrot is secure. And Carrot will notify you when it's time to update your carrot. We've put a lot of work into Carrot and can't wait to share it with you. Carrot, a simple way to stay alive.
All right, so what's the joke there? Explain the joke to me. Pretend I don't understand. There's a number of jokes, but somebody explain the joke to me. Yes?
Even the simplest things can be marketed well.
Okay, so even the simplest things can be marketed well. We'll have a marketing lecture coming up here in a few weeks. Please.
It takes a lot of things that people usually use to market or value about new sides, like simplicity, innovation, like smoothness, and like put it on a carrot. So
Yeah.
it sounds ridiculous.
About the only thing they didn't say is that it's disruptive. Yeah. What else we got? Yep.
One of Apple's ads very clearly follow the same beautifully minimalist design and over-exaggerating anything and everything they say to make it sound extreme.
All right, so it's quite specifically poking fun at Apple. That's clear. Yep.
They use like gestures, which use on like smartphones to make it seem like it's some sort of technology product, because I guess every product that comes out these days is kind of like some form of app or technology. So they're kind of playing off of that and making it.
Indeed. So that might be why it's in this lecture. Part of the joke is that people understand so deeply, this swipe up, swipe left, swipe right, swipe down sort of lexicon, that it's very easy to just play off of that and satirize it. So there you go, introducing Carrot. So the topic today is input devices. And why are we doing this? Basically, input devices is the next to last, that's not quite true, the next to last of the like big core HCI concepts that you just like cannot get away from within the field. So if you look at like the big HCI conference, which is called CHI and happens every year, it's happening this year in Seoul, South Korea. They have multiple tracks, and like one track is all about like prototyping. That's Thursday's lecture. One track is all about like novel new displays. One track is about research methodology. One big track is about input devices. And so this is just the sort of thing that you need to know. Even though I admit that like right now we're in kind of a lull in kind of interesting things happening in input devices. Something exciting is bound to happen soon, and exciting things have happened in the previous decade. So we'll kind of walk through those and see what's interesting here. All right, so at a high level, what you're trying to understand about input devices are what are the tasks that users are trying to accomplish with the input device. And here we're talking about task in a different sense than the like task analysis sense. Here we're talking about tasks in a very like micro sense. You know, they want to click, they want to point, they want to select, things like that. What do we think about like the space of possible input devices? So what can we look into the world and say, here is an input device that hasn't been invented yet, but that I could invent? And then what interaction techniques are kind of encouraged or discouraged by particular input devices, by phones or by mice or by tablets or by whatever. All right. And so we're going to focus today on kind of two high-level tasks. One is text entry, and the second is pointing and marking, and then everything that comes with pointing and marking, like target acquisition and steering and freehand drawing and drawing lines and tracing and things like that. There are many other low-level tasks that we could study here, but these are the two that we're choosing to focus on today. Just imagine while we're going through this that if you were to pick another one of these like big buckets of tasks, it might be interesting, say on a midterm or something, to focus on how this same methodology applies to some other sort of task. So this methodology applies across a lot of devices. All right, so we're going to start with text entry, keystroke devices. And here the fundamental concept is that you have an array of discrete inputs. There are lots of different ways of doing text entry, and we'll talk about lots of those. Various sizes, various configurations, but the vast majority of keyboards out in the world of the like physical hard variety are still two-handed keyboards that are in a QWERTY layout, at least in the United States. And elsewhere in the world, they're kind of two-handed keyboards in whatever the regional layout is able to toggle over to QWERTY for other types of input. And if you remember our lecture on model human processor last Thursday, and why wouldn't you? It was thrilling. You will recall that like keyboards should, by model human processors model of the world, be sort of impossible. Like text entry and like the things your hands do just can't work if you're having to perceive and then be cognitive and then be motor processing every single little move of the finger. But if you remember from that lecture, we talked about how really when you try to do something with your hands, it gets chunked into these like things that your brain has pre-rehearsed. And that's what typing involves. So like speed touch typing is about transferring these like big chunks of data from your head to your hands and then just letting your hands kind of semi-autonomously do their thing. Which is, of course, the reason that you will often find yourself making these slips where you start typing the word that you mean to type and then finish typing some other word. And it's just because something got screwed up in that like chunking process and you type a more common word instead of the word you're going for. But anyway, this follows this power law of practice thing where like the more you work with a keyboard, the more used to it you get, and you get this kind of curve of like how people type. How fast people can input text over time. So keyboards, up here we have like a classic keyboard. Down here we have a wacky virtual laser keyboardy thingy. That's a BlackBerry. Who remembers Black? No, I'm kidding. That was BlackBerry. These were really super popular for like a year, and I don't know if anybody even remembers them anymore. But for a while, like there was this thing where everybody thought the way you were going to input text in phones was to like keep this thing strapped to your wrist all the time, and then you're going to be like, and then it would show up on your phone. That didn't last, it turns out. Folding keyboards, very exciting. So somebody tell me, here we have just two plain old keyboards. Keyboard, virtual projecty keyboard. What's good and bad about this projecty keyboardy guy? Please. Yeah, so you have a very strong human factors problem here, which is that you lose all the haptics of the keyboard. And when you're going and typing on this thing, you don't know what's going on. It's sad. Yep.
You don't also feel relativity where, you don't feel the F and J key.
Right. So if you were typing on this thing and like looking over here, you could easily just like literally drift off the keyboard, which is not really a threat with a conventional keyboard. Yep.
So I think based on an angle, then facing the keyboard and it's no longer one we normal.
Yeah, you got like a keyboard,
It's going to be a lot larger than the function key.
right? You've got like a keyboard keystoning problem, which is curious. Yep.
It looks like it would be portable, but on the other hand, it requires a flat surface.
Yeah, so it's kind of sort of portable, but wherever you could put it, you also could like put your keyboard there. So not super exciting, although they're cool, like to show to people. And everybody that sees one of these thinks of like some cool new product that you could only build with that thing. So hey, it's something. One of the big issues around text entry is ergonomics. And so there's this whole world of ergonomic keyboards out there. They vary in wackiness from like mildly wacky, like the Microsoft Natural, which I probably is the best-selling ergonomic keyboard in the world because they're all over the place, to like things like this, which you actually do see out in the world. Like people use these ones where they're all concave in and your hands rest down in them, all the way up to like the really truly trippy wacky, which are these things. There's a whole class of keyboards out there that are broken into chunks, and the chunks are like individually spring mounted and servo controlled. And so they try to kind of track with your hands while you type on them. There's also a whole world of like Star Trek-y split keyboards where you have like one over here and one over here while you're sitting back in your chair. Those are kind of fun. Anyway, an interesting consequence of ergonomic keyboards is that they are somewhat difficult to learn. So if you are used to typing on like a laptop and then you go and you jump onto a Microsoft Natural, which is really a pretty tame keyboard, it still will slow you down drastically. So getting used to these things is tricky, and it kind of breaks your muscle memory. So there really is kind of an association, not just between your brain and like the act of typing, but between your brain and a particular keyboard. It's kind of cool. So key layout is a big issue. Who here, if anyone, has ever tried to learn the Dvorak keyboard? Some of you. It's like the sort of thing you do in high school when you're bored and everybody else is bad at computers and you are waiting for them to catch up. So this is QWERTY. It's what we're used to. This is the Dvorak layout. QWERTY was introduced in the 1860s with one of its goals being to try to alternate keystrokes between hands. So the way it was for typewriters and the way that typewriter mechanics work, if you hit two keys on the same half of the typewriter at the same time, the arms would sometimes conflict and cross. And so it was ideally trying to get you to move as much as possible, alternating between hands. Some people will tell you that it was made specifically to slow you down. I don't think that's actually true, but I do know that it was made to get you to alternate between hands. But now we don't care about that. We don't care anything about whether we're alternating between hands other than that perhaps it's good ergonomically. And so Dvorak at some point, which probably says pure, nope. At some point Dvorak went about the business of trying to make this thing more ergonomic. And there's a lot of things that he did there. So he tried to make the most common letters easiest to type, so putting the most common letters on the home row. Tried to put like useful combinations near each other, so like T and H are right next to each other. And then the most interesting thing, I think, is that he studied how English works and like how letters combine to make words. And he tried to do this thing where words, as a general rule, are supposed to move from the outside of the hand to the inside of the hand. So if you look at like typing the word the, it's supposed to move this way. And there's a classic human factors experiment you can do here. So if you have a flat surface, try sitting there and do this, and then do it the other way. And it's supposed to be easier to roll from the pinky to the thumb than the other way. It says it's true in the book, so we're going with it. Cool, so that is that. The problem, everybody's actually using mobile devices right now. So we spent like a century figuring out text entry on like this form factor. And now all of a sudden, like nobody's using it. And we have to go back and kind of reconsider the entire world of text entry to be for the mobile space. And so it's still hard. It's a mix at this point of on-screen soft keyboards and some thumb keyboards, although there are not a lot of them. What percentage of the class has ever owned a phone with a physical keyboard? Okay, what percentage owns one now? Yeah, nobody. There's not a lot out there. It's sad. I like them. This is the last one that I owned. It's just the Motorola Photon Q, which was big 2 years ago. And it was kind of the last like hurrah for the slider keyboards. There is this huge group of people out in the world that still use the Samsung Epic, which was a Galaxy S1 phone. It was in the S1 generation. It was Sprint's version of the S1, and it has what is widely considered the best ever keyboard on a mobile phone. And so there's all these people out there that like still trade these things and keep them repaired and use them because they just really want the nice keyboard. Alternatives include things like full handwriting recognition, graffiti, edge write, swipe. We'll talk about a little bit of those. But first, we're going to go back to the 90s and talk about mobile text entry on keypads. So, a few people remember the 90s. Hooray. So the 90s was very bright and neon. If it helps you get into context, think medium-sized hair, but lots of bright colors. So basically, this was what phone keypads looked like in the 97, 98, 99 sort of era. And if you're of my generation, you can imagine what is around this keypad. It's like a Nokia stick phone sort of thing. Like this screams 1998. And the way you typed was that if you wanted to type a B, you whacked on the 2 a couple times. And then if you wanted to type an A after the B, you waited a second until the cursor stopped doing whatever it did and told you it was ready for a new input, and then you tap 2 again to type A. And so it was really fast if you needed to type like A, G, J. But sadly, that's not a word, and so very rarely was that typed. And if you needed to type like mom, screw you, like that just will take forever. So that was the way those worked for a long time. And then somebody, and it probably even tells me who here. Nope. Somebody came along and invented T9. Who remembers T9? T9 was cool. So T9 was a predictive text mechanism where you just hit each key once instead of doing the doot, doot, doot thing. And then it looked in a dictionary of common words and it tried to predict what you were trying to type. And for like 3 years, texters used no slang because it took too long to type slang. And so like everybody spoke really proper English for like 2000 to 2002 because T9 was deciding what you were writing on your phone. It was a special time. There's an idea that is like as old as computers, basically, that people have tried recently to bring into the mobile space, and that is the chordal keyboard. So the idea here was that, so this is a very early mouse. This is a keyboard, but what the hell is this thing over here? That's a chordal keyboard. And the idea was that instead of having like a shift key and an alt key and a control key on the keyboard, you would break it out and make it its kind of own thing so it was very easy to find. And so you would be either typing on the keyboard or you would be chording with your mouse. So instead of like a right, although this one actually has right, left, and center mouse buttons, but you could do additional things with the mouse by doing something with your left hand while you're doing something with the right hand. As you can imagine, just by looking at this, it didn't take long before somebody started doing foot pedals, and then somebody started doing like eye tracking, and somebody started doing shift your weight. It's called a postural interface. And there's all sorts of like different ways to do this chording that is interesting. Like really, the people who invented the mouse assumed that this was going to be the way people did input, that like chordal keyboards were going to catch on, and they just really didn't quite. Although now, as like mice buttons fluctuate back up and down, we do see more of the like hold down shift and hold down control and things like that, like on the MacBook, for instance. So chordal keyboards, somebody thought a while back that, boy, chordal keyboards would be a great way to do text entry on mobile. Thus was born this thingy. And so what this is a keyboard entry, a text entry mechanism. It's a little hard to see here, but basically you have individual keys for like the 1, 2, 3, 4, 5, 6, 7, 9, 10, 12 most common letters. And then if you want any other letter, you hold down some combination of 2, okay? And boy, that sounds complicated to me, but apparently they sold some of them. So good for them. There's like a chordal thing over here where you hold this down. This I don't think caught on. I'm sad to say for whoever built the Twiddler 2. But good idea, worth trying. Why not? So talk to me about soft keyboards. This is kind of where we're at these days. This is SwiftKey, and it's probably the most popular keyboard on Android. What's good and bad about it? Yep.
The good is that it has predictive text, and not just normal predictive text, but it hooks up with your Gmail account, Twitter, Facebook, everything, and it picks up your common phrases.
Okay.
And it throws it into its dictionary.
So it's theoretically good at predictive text. Yep. Yeah, so the haptics of it aren't great. Agreed. And you can easily just kind of drift off someplace. Yep. Yep, so you got the fat finger problem where you might accidentally hit too many keys at once. Yep.
So when you don't want it, it's not that you can always, you have an entire phone for whatever you want to do, and when you want it, bottom.
Yeah, so it comes and goes depending on whether you need it, which is a pleasant thing. Yep.
For Android phones that like have a lot of variance in size, that also affects the size.
Mm-hmm. Yeah, so that's good and bad that these things are like dynamic. So people make some interesting keyboards where, you know, for tablets, for instance, there are ones that are split. There are ones that are, you know, in various interesting shapes. I'll show a couple of them here in a minute. But the feedback thing is a real problem, and it does tend to lead to these things not being eyes-free. You kind of have to be looking at what you're doing. There's also this issue where you're mostly typing with your thumbs, and it's good and bad. It's very easy to rehearse, which is why people get really fast once they're like comfortable with the texting system, but it's rather difficult to learn. So there's that. It used to be that everybody just assumed that handwriting was going to be the primary entry mechanism for text on mobile. So we're going to talk at least a little bit about that. The classic example of this was graffiti on the Palm Pilots. And with graffiti, they tried to address this problem of you can't write across the device because we don't have a digitizer that like can handle that. So you're going to have to write in this little box here. That's how this worked. And we're not really good at recognizing like arbitrary people's handwriting. So we're going to tell you what letters look like. And by the way, we're going to tell you what letters look like in a way that doesn't really look like letters, just because it's faster and it's more predictable. So you end up with this vocabulary of here is how you write letters in graffiti. And so like the A loses its crossbar and the F loses its crossbar. I is you've like always had to write lowercase. the way this worked was there was only one case of letters. You always wrote them in this case, and then you did a special gesture if you needed the case that it didn't think you wanted. Same thing for numbers, like the numbers get a little wacky here. And so anyway, they basically invented a grammar for interacting with the device, and people learned this. I mean, people got good at this in the same way that people are good with like texting today. People got good at graffiti. But it kind of went away because there were just other better options. EdgeWrite was a big HCI kind of research project that never saw practical application as far as I know, but did really kind of change the way people thought about handwriting entry. And the idea here was that instead of having just a flat open space, you confine the space so that the stylus can kind of follow the edges. And then again, there was a vocabulary, but it was, you know, a grammar for interacting with this thing, but it was all based on the edges of the screen. And this, people got really super fast at. Like if you used EdgeWrite as your primary input mechanism, it was not comparable to typing, but it was close. Like it was pretty damn fast. Yep.
So would you have your device and then you would buy this little plastic thing?
Basically, yeah. So it was just a little plastic guy that you slapped on top of the Palm Pilot. So EdgeWrite, very cool. Nowadays, the kind of popular thing is gestural, quasi-gestural
At the
text
letter
entry.
T, pressing my finger against the phone here, going to the letter I, P, with my finger still on the phone, down to S, and releasing my finger here. There is one swipe, the word tips. For the word and, let's start at A.
Okay, you've all seen swipe before. So who here, we'll have a vote. Who prefers typing with predictive text, something like SwiftKey? Who prefers swipe? Okay, so I'd say SwiftKey's got about 3/4 of the room, and swipe's got the last quarter, and of course SwiftKey at some point put in swipe, which apparently wasn't patented. Anyway, so this is a text entry method that is quasi-intuitive. An interesting HCI test would be to go out and try your friends and see who's faster with different mechanisms. What you will learn more than anything is that if you make somebody change away from whatever they're used to, you can really screw them up. So like you can really slow down somebody's typing by forcing them to use swipe if they're not a swipey sort of person. So you can go out and do these sorts of studies. And back in the T9 era, there was a big study of, if you have somebody typing on a regular keyboard versus a soft keyboard versus T9 versus handwriting versus the Nokia multi-tap sort of thing, what does performance look like? And it turns out that, experts on a real keyboard hover around 70 words per minute. On a soft keyboard and on T9, pretty comparable. They hover around the mid-40s. Handwriting is hard to do on a phone, and multi-press thing was awful. What I like about this chart more than anything, though, is how fast people got at that stupid multi-press thing. Like that people got up to 27 words per minute on those Nokia phones is amazing to me. And I was of the age where I should have learned. Apparently, I just missed out on that. Thoughts, questions? Cool. So one thing I want to emphasize here is that the fight is not over here. Like while there are a couple of dominant mechanisms, being basically predictive soft keyboards and swipe, like there's still interesting stuff going on here. On the Android store today, if you search for keyboards, there's like 1 billion different interesting keyboards that people have invented that cover the gamut from like regular keyboards with slightly different styles to like crazy, wacky things. I'm going to show you just a couple of them here real quick.
We've released the first version of the Minium keyboard to the 10,000 amazing people who supported our Indiegogo campaign. Here's a quick look at how Minium works. Minium uses the same keyboard layout you're used to, just minimized, so you already know where the letters are. You don't have to hit each letter precisely. Simply aim in the general vicinity of the letter, and Minium will know what you meant to type. Typing the word happy, even though I typed HWOKG, Minium knows that I wanted the word happy. If Minium's first suggestion isn't the word you had in mind, you can choose from other suggestions here. To space, slide to the right. To delete a word, slide to the left. You can slide and hold to explore other options like enter and settings. When you do need to be precise, when you're entering passwords or unusual words, Minium comes with an easy zoom view. It lets you precisely select letters, or numbers, or punctuation. When you type an unusual word, Minium will learn it for next time. Not only does Minium learn from what you type, but it also predicts the next word that you might want to type. For access to other features, press and hold the Shift key. You can switch to uppercase, numbers mode, you can change the settings, or choose alternate keyboards. You can also just quickly switch between letter and number modes by flicking down on the keyboard. In numbers mode, you also have access to additional symbols. If you can't live without a spacebar, enable the spacebar option in the settings menu. And that's it. The Minium keyboard is that easy. We're beta testing with our supporters right now, and if you're one of them, we'd love to hear back from you. If you missed our campaign, you can still join the next phase of our Minium beta by signing up at minium.com.
All right, so that's one. What was their main goal, you think? Sure.
Kind of to reduce the amount of space on the screen the keyboard takes up for smaller phones.
Yeah, so just to kind of shrink the keyboard while still maintaining, as much usability as they could. It's interesting, fun. Here is something completely wacky that I found from the Kai 2014 input devices track. So this was just last year. Just watch this, it's interesting. So if you don't get this, they're not comparing these two things as text entry mechanisms. They're saying that you can use one keyboard for typing and then also for gesturing for other purposes. So they're not saying like gesturing is better. They're saying here this is how you classify. So if you're like training a machine learning algorithm to recognize the difference between typing and gesturing, that's how you do it. Yeah.
So SwiftKey has like a swipe feature, and for April Fools about a year or two ago, they got the swipe feature and put it on their website. You could actually go and still try it. So
fun.
Unless you swipe with the physical keyboard.
So anyway, what these people are suggesting that you do is that you be able to type and then you flip over and say you want to open a new document. You can do the gesture for that. And they can recognize the difference between those two things and classify it and then do the right thing. But I think any input mechanism that involves just across your keyboard is fun.
Are they pressing all the keys while they do the dot?
I think so. I assume so, that they're just holding down the keyboard and going. We'll go back to their music for a second, just to. you get the idea. So interesting things still going on in the input space. One of them that keeps coming and going is speech recognition. I love this lady, by the way. I found that picture last night. I was very excited about it. So dictation is fast. That is a good thing. You can get up to an easy 100 words per minute dictating. So why hasn't speech recognition like dominated the world?
It's not accurate enough.
Okay, so there are accuracy problems, although that's improving. Traditionally, there were horrible accuracy problems, but it's not as bad anymore. Yeah.
Sometimes you still want people to hear you.
Yeah, so I think more than anything, speech recognition has been battling against the trend towards open offices. Like, if you have 20 people sitting in an open office space, like working on things, and everybody's like, computer, turn on, it could get really weird very quickly. Where is speech recognition actually like doing well? There are a few places. Sure.
Well, you might disagree with this, but if you call customer support and it gives you the options, I totally hate it, but I guess you could argue.
Sometimes it's okay. So these things, I don't know that we're going to do speech user interfaces in this class, although we might. I might put a lecture in about that near the end of the semester, just because it's interesting how those work. But yeah, if you kind of have some idea of what somebody's going to say, then speech recognition is much more accurate than if you're just guessing from all the possible words in the language. Yep.
Smaller devices like phones without the keyboard.
Yeah, so people do use it sometimes on phones. Siri uses it, and Google Now uses it, and Google's using it as an excuse to listen to you 100% of the time all day. There's an interesting lawsuit going on in Europe right now because I'm not going to name the manufacturer because I'm not positive I know who it is, but somebody got in trouble because they were recording all the audio from your living room to decide whether to turn your TV on and off, things like that. And then they just like sold all of that data to third-party advertisers. Turns out people didn't love that. Yep. Yes, I think it was Samsung too. But yep.
It'd be useful in like cars where you can't use your hands.
Okay, so speech recognition is doing really well in cars. The other place where it's kind of doing okay is with the Kinect. So like the Kinect on the Xbox One is still kind of a thing. And so using it for like home automation control within the context of like your own house is doing okay. We got most of that. This is the one other point we should emphasize here is that speech is very different from written language. And so like writing a research paper, for instance, with speech is really difficult because you just don't talk that way. You don't talk in kind of the same cadence that you write a research paper. And getting yourself to verbalize in that cadence is really, really challenging. It's a good cog-sci problem for you cog-sci people out there. Yep.
The problem I have too is like if I'm trying to dictate a text message or something like that, I'll like change my mind about what I'm saying or like kind of pause and like think about it for a second and like use ums or whatever, and like the voice recognition software can't figure that out. That I'm thinking or pausing or changing what I'm saying and saying never mind, don't say that.
Yeah.
And it just literally does everything I'm saying.
Right.
So
yeah, so there's this serious kind of cognitive burden of trying to present information to the speech recognizer in a way that's meaningful to it. Please.
I also thought it was really hard to like, ask a question, have a question mark at the end.
Yeah.
I think about punctuation when I text, so I think that's something Siri still has to pick up on.
Phones aren't quite so great at inflection. Yep.
Do you know how well speech recognition works on people who like have first languages and language?
Not great. Even with limited vocabularies, it's not great. So like accents are a problem, and as you suggest, people who kind of think in another language often have trouble using speech user interfaces in a lot of different ways, both because it comes out weird and because you get more of these like pauses and ums and etos and whatever language you're thinking in. Cool. All right, moving on. So we have covered the text entry part of this. Now we're going to blaze through the pointing, marking, target acquisition part of it. So mice are kind of the canonical pointing device, and what we're going to start with. The most traditional, the first mouse looked something like this. It's just like a steel wheel inside a wooden box. From there, we've gone all the way up to like gestural sort of selectee input devices to things like the leap motion. So we have these sort of notions of like 2D versus 3D pointing and clicking selection sort of devices. But despite all that, the most popular in the like desktop computing space remains the mouse. And so I want to talk just very briefly about how a mouse actually works, because this is for HCI kind of where the rubber hits the road. It's the like actual moving from things happening in the real world into ones and zeros. I think that's kind of interesting. For argument's sake, we're going to talk about ball mice. I took a bet in my office yesterday. What percentage of people here have actually used a ball mouse? Okay. About half. 2/3 maybe. Not bad. Optical mice, I think, started dominating around 2000, 99, somewhere in there. Anyway, so the way this thing works is there's physical buttons, actuators, like 1, 0, complete the circuit sort of buttons for the left and the right. And then there are these encoder wheels for the scrolly bit. And how does that encoder wheel scrolly bit thing work? It's kind of interesting, so we'll talk a little bit about it. There's an IR emitter, so this is an IR LED, and then an IR detector. And there's an encoder wheel. And the idea is that as the encoder wheel spins, it breaks the beam between the IR emitter and the IR detector, and you get this wave. So you get a waveform as this thing moves, and you can tell whether it's high or low, okay? And so if we're looking here, we can say, okay, this thing is high right now, good. And then if I rotate it this way, and I sample at some steady sample rate, I will see that, okay, it was high and now it's low, so I know that motion happened. But we have a problem. These things can roll in either direction. You can scroll up or you can scroll down. And so if you scroll backwards, you get this same transition from high to low. How do we know the difference between those two things? How can you tell the difference between scrolling up and scrolling down using a rotary encoder? Anybody? Yep.
Some sort of extra thing that senses which direction you're hitting in?
Nope. Yep.
Use your receivers and gotcha.
Yep. All right. So you have to put 2 receivers out of phase. That's the general solution to this problem. And so you're looking for these weird situations where they're not both the same. So you have one of them low and one of them high, or going the other direction, this one low and this one high. And from that, out of phasedness, you can build this transition table where if you were at high, high, and you go to low, high, you know you were rolling up, and vice versa. So this is a very practical, physics plus logic plus computer science equals input device sort of thing. We're not going to deal with that much in this class, but be aware that there's all this engineering work that goes into making these things actually physically work. And then what we want to deal with is usually the higher level abstractions. How did ball mice work? How did you actually do the XY bit of that? Yep.
Ball rolled rotors which spun the slitting circles.
Yeah. So the ball here rolls these 2 rollers on either side that turn the encoder wheels. And so you get an encoder wheel for X and an encoder wheel for Y. And you take the X component and the Y component and you plot it out to coordinates on the screen. How do optical mice work? Well, there's a hint in there. Yes, optics. All right, so optical mice are just tiny, crappy little cameras, and they're looking at the surface of whatever you have them on, and they're recording it. And so somebody a while back did this kind of famous little art project where they kept track of everything the mouse could see. You could actually get to that in the driver for this one particular brand of mice. And so you could put it on like a piece of paper and like drive your mouse around and like very, very slowly scan a document by just driving your mouse over it. And the basic idea here, the way it works, is that it's taking a picture and then it takes another picture a microsecond later, and it looks for what direction pixels are moving. Basically, it's a computer vision problem to figure out where the vector is in the space. Incredibly complicated solution to a rather simple problem, right? Like you had to basically, to invent the optical mouse, you first had to invent computer vision, which is interesting. Yep.
When you pick up the mouse, why does the light get brighter?
Light gets brighter because it's trying harder to see. So it's losing track of the surface, and so it's trying harder to see what's going on there. The reason for the mouse, for the bright light, is that most of the time you're running these mice over rather homogeneous surfaces. Like you're not usually doing text. And so it has to look for like really microscopic changes in the surface. And so it shines this bright light on it to get the best contrast it possibly can on what's going on the surface. Yep.
Why the color red?
That I don't know. Presumably it's best because everybody settled on it, but I don't actually know why it's best. Every now and then you see blue optical mice, but definitely red dominates there. I'm sure there's a physics explanation for that. Somebody look into that. Let us know. All right, so in your typical mouse, what are you sensing? This is a like classic diagram. Really, you're sensing just movement. So the key thing here is that mice are relative devices. So unlike, say, a touchscreen, where if I touch here, I mean here, with a mouse, you are instead putting a vector from your present location. And so you can move the mouse and it'll move in that direction, and then you can clutch. You can pick up the mouse and move it someplace else on the mouse pad, and then you can keep going. Yep.
Do gestures make touchscreens relative devices?
Yes, in a sense. So if it matters, kind of like, if it doesn't matter where you're touching on the device for the input, then really you're entering keystrokes instead of doing a pointing task, ultimately. But like if it matters where you're pointing, then it's still an absolute device. Okay. So other device properties are things like, is it direct or indirect? Is it relative or is it absolute? Do you sense rotation? Do you sense delta rotation? Do you do force or delta force? There are a few like key joysticks that people use that are kind of force-based rather than position or movement-based. The cursor to display ratio is a big deal with these sorts of things. So how does this get reflected on like a desktop computer? What do I mean by cursor to display ratio? Yep.
Like how much you move your mouse on your mouse pad versus how much you move the display.
Yeah, so it's just the mouse speed, like that setting in your control panel somewhere that says, if I move my mouse X amount on my table, I want it to move X pixels on the screen. And very rarely is that one-to-one. Like you wouldn't, if you have a 24-inch monitor, you wouldn't want to have a 24-inch mouse pad to like access all of the space on your screen. And so, you know, you get that sort of thing. The obvious question is, what is the cursor to display ratio for touchscreen input? 1-to-1. But you do sometimes see other wacky solutions, like when people have external touchpads for mobile devices or things like that. It does happen. And then the last kind of device property I want you to be aware of is device acquisition time, which is all about how long does it take you to like get into position to do the input. So how long does it take you to like get the mouse and get where you want it to be, or pull out your stylus or whatever? Yep.
Does the C to D ratio for direct touchscreen input like take into account the fact that you have a fully calibrated touchscreen?
That would just be a broken situation, I would say. Like it should be 1-to-1. Back in the like digitizer day, it wasn't always, but these days it's a pretty safe assumption with these things. Like just basically the way they work, they almost have to be right. Yep.
Is the CD ratio for nice variable?
Yeah. So I mean, it's just a setting, right?
Well, aside from the setting, like if I set it to be a setting, but I move the mouse slower, it travels less across the screen.
So that's also a setting. So that's something called mouse acceleration. And so you would expect like I move the mouse versus I get pixels on the screen ratio to be linear. But it turns out that on most systems it's not. On most systems let's see, I have to get this right. I think it starts slowly and goes up pretty quickly. So like there's a mouse acceleration curve. If you buy like fancy gaming mice, they will give you this curve with like lots of handles on it so that you can like adjust that curve to be however you want it to be. So maybe you want to at certain speeds move really quickly across the screen, but at certain speeds move very slowly. For all you StarCraft players, there's a sweet spot in here where like you get just the right amount of mouse movement speed. Anyway, any other questions on that? Yeah.
Would it have an interface within the interface? Like in a lot of video games, they would give you like a touchpad on the screen, which would move a cursor on the same screen, but it's not you touching the cursor itself.
Touchpad on the screen that would move a cursor on the same screen. Give me an example.
So I mean, if you think of like a laptop's touchpad,
Mhm.
and you just designate an area of your touch screen to act as a touchpad. It's still a touch screen because you have stuff.
I see what you're
happening
saying.
underneath it.
Yeah, so that would be indirect and relative, like as all touchpads kind of are.
So I mean, the reason I ask is because you can't classify necessarily a touchscreen as one or the other. It's kind of
Sure, it's however it's being used, right? And so there are wacky things you could do with that. Have you ever used a Wacom digitizer, like the tablets that you use for like drawing in Photoshop? Those often have just a switch, either physically on them or in the software, where you can switch between relative modes and absolute modes. And it's useful for different things, right? So like sometimes you want pixel to pixel sort of mapping between your input device and the screen, and sometimes you don't. Sometimes you want to be able to move relatively. So different tasks have different, suggest different interaction methodologies. It happens that the mouse is really effective for a lot of them and that relative motion is really effective for a lot of them. So that's kind of one out in general. But for specific tasks, people use other things. All right, moving on. So trackballs, anybody use a trackball routinely? Has anybody before? A few people, handful, half a dozen. How about the trackpad? Do you like your trackpad? Okay, very good. So trackballs are indirect relative motion. It's basically just a mouse turned upside down. Trackpads, 2D relative motion, along with some force sensitivity sometimes. So some trackpads do different things based on how hard you're pressing down. Okay, who remembers the track point? Who's a fan of the track point? I like the track point. There are 1,000 names for that little guy. So this is a indirect force sensing velocity control sort of thing. Fundamentally, it's a joystick. And it has a very, very nonlinear transfer function. So as we're talking about here, this curve can be wacky. The curve with the track point is particularly wacky. So if you touch just a little, you get just a little. And if you push a lot, you get this. And then there's this big jump where it goes back to linear again. So a lot of thought went into kind of how to use this device and how to make it behave the way you expect it to. Anything else interesting there? People do really well with it. Like what killed it? Mostly the trackpad, I think. Like trackpads just came to dominate, and I think that mostly it was that Apple came along and did the trackpad better than IBM had done it and kind of took over that space. I don't know, if you buy a new ThinkPad, I know you get viruses and superfish. Do you get the track point still? Yes?
Yeah.
Good. Good for them. Good for Lenovo. Cool. So that is still there. How about on mobile? How do pointing tasks happen on mobile? Mostly touch. There have very recently been a number of other options, though. Anything else other than touch? Some stylus is still out there. Yep. Okay, so orientation is sometimes used for selection. True enough. Yep. Okay, so like volume rockers and things like that, various rocking solutions. Yep.
Like virtual reality stuff, like for your turn too.
Okay, so augmented reality and like the accelerometer-based sorts of things. Yep.
Some devices, LG, Samsung, have the eye tracking. It's just cool.
Okay. Eye tracking and gestures, and like Samsung does their like air, whatever they call it. Doesn't work for me. Cool. So one thing that we didn't mention here is D-pads, which really not very long ago were a big deal in mobile. So like BlackBerry had what they called the trackball for a long time, which was this like little wheelie doodad that sat in the middle of your phone and was used for pointing tasks. And then even just as recently as like the most recent, the last generation of the Droid phones, they had these D-pads where you could do left, right, up, down, enter on the D-pad. Direct touch is obviously a big part of it, and then styluses, styli. All right, Fitts law we talked about last time. It's this notion that the time it takes you to move the mouse from here to here and acquire this target follows this very fixed power law. I want to talk very briefly about the kind of design implications of Fitts law. And the big parts of it are bring items closer to the cursor, make them bigger, and exploit the edges. So an example of bringing items closer to the cursor is the like context menu in Office. So it used to be that if you wanted to change the font of whatever you were working on in Office, you had to select it down here and then go up to the menu bar and select whatever you wanted and then come back to your task. At some point, Microsoft decided they were going to move that little fonty window right over your cursor when you hovered for a second. And that's a good thing. It brings the target closer to you. It speeds up the time it will take you to acquire it. Much better. You see a lot of this in kind of circular menus, which were popular for a while. They kind of come and go, as with all interaction design. But like bringing targets in closer to your mouse is a good thing when you can do it. The uber example of like the most Fitts law-y interaction technique in the world is the pie menu. So instead of taking this like long list and putting it like this, you spread it around a circle. There are two advantages to this. Who can give me 2 reasons pie menus are great?
Well, I mean, one is that you don't have to move as far to
Okay.
your option.
One is that it's very close. Yep.
All options are equal distance.
Okay. All options are equal distance, which is cool. There's one more big one that you might only know if you've like actually used software with a pie menu. So you are looking at a pie menu and like your mouse pointer is right here and you've got the pie out here and it's got its little wedges. The thing that's not obvious maybe is that these targets are actually infinite. So all you have to do is gesture in a direction and let go of the mouse button. And it doesn't matter whether you actually hit this wedge or if you hit someplace out in its like extended infinite wedge, you get the same thing. And so you get like infinitely good Fitts law results because you have an infinitely large target. And it's actually true. It actually really does work that way. So that is good. A lot of work has gone into increasing the size of buttons for this purpose. So back in the like Windows 98 sort of era, icons always looked like this, just these like little tiny guys up in these ribbon bars. And those have kind of faded away in favor of like big things with art on them. And it's easy to imagine that this was strictly a sort of aesthetic design decision to go towards something with a little more color and shape and feel to it. But the reality is that it was also an excuse to make the targets bigger and make them easier to acquire. So that is cool. The classic Fitts Law thing is making use of the edges of the screen for this exact same reason, that you end up with like infinitely large targets in a direction. And so compare the difference between the Windows 98 start button and the Windows XP start button. I will claim that this one is infinitely better than the other one. And it's because if you threw your mouse all the way to the bottom left corner in Windows 98 and tried to click, you didn't get the button because there was this stupid 1 pixel border around the bottom left hand of the button that wasn't part of the button, and so you couldn't click it. But in Windows XP and all further ones since then, they put it all the way in the bottom left so that if you just throw the mouse in that direction and click, you end up getting the target that you wanted. Same thing happened with OS X. Like in the first version of OS X, they made a big deal about Windows used to, in Windows XP and such, a Microsoft window looked like this, where there's this title bar and then the menu. And if you clicked up here, you could like drag the window around, but you couldn't actually interact with the menu. And then somebody decided, hey, we should move that menu bar all the way up to the top so that you can throw the mouse to the top of the screen and get the target you want. So anyway, that was good. And yeah, everybody's happier now. Yes?
I just noticed that practically at all at the top because it makes less semantic sense. Like, why would it be there?
Yeah, I have mixed feelings about it too. I understand. But it is undeniably easier to acquire as a target. All right, does Fitts Law apply to mobile devices? Or should I just pull all these slides out of here and stop talking about Fitts Law because we live in a mobile world now?
I think it does, because it depends on the size of your icon.
Yeah, so if anything, actually Fitts Law applies better to this. So the original experiment, the Fitts experiment, was actually about human arm movement. It was about hitting physical buttons. It was about like, there's a button over there. How long does it take me to actually like reach over here and hit it? And the work of Card and company back in the 70s, late 70s, that expanded this notion to like mice and digital representations of pointing was actually a novel result. It was not at all obvious that that should be true. So Fitts Law is actually really all about physically moving your arm and pressing things. So if anything, it applies better than it ever has before. The main difference is what you lose on mobile devices is that you lose the benefit of the edge. So you can no longer kind of throw your hand to the edge of the device and get that like infinite space. And for most common interactions, you have this fixed like cursor to display ratio where you're just inputting directly. Yep.
I would say that there are also like examples where you don't lose this functionality, where some of them have swipe from the edge, which you have the edge still to start
to work from. Yeah, so you can still kind of use it as a like finding where to do your gesture thing. It's not quite the same as like target acquisition, but it is interesting for like finding where to do things. All right, we're going to dig next into a little bit of what was in your reading this week. So if you remember these like fancy state machines, this all comes from work by Bill Buxton. And if you're interested in this topic, like if input devices are a thing that speaks to you, he curates a collection of like every input device ever. And one, he actually travels with it. He often brings it to Kai, and it takes up like a room this size. It's a museum sort of gallery where you can like walk around and be like, ooh, the Power Glove, that's so bad, and things like that. If you don't get that joke, go watch whatever movie that was. All right, help me, somebody. What's the movie with the Power Glove and the kid? The Wizard? I think it's called The Wizard. Anyway, go watch that. So he travels with it, which is very interesting. And then there's also an online version of this. So if you just Google like Bill Buxton, wow, don't Google it. He would be pissed that I said that. He works for Microsoft. If you Bing Bill Buxton input devices, you will find this collection digitally online. All right, so the first thing to understand about input devices from a kind of formal theory perspective is that usually applications only care about input devices as logical devices. So from the application's perspective, we care about things like mouse down, mouse up, click, double click, right click, which is very different from the sort of like fundamental Buxton model. Well, it's very different from the actual physics of what's happening, right? Like the encoding and how the sensors work and all that gets abstracted away from our perspective. And you end up eventually with this three-state model of input devices from Buxton and Hinckley and company, where the three fundamental states he claims of a input device are that it can be either out of range, it's not physically tracking, it can be tracking the cursor, or you can be like actively in the act of interacting with the screen. So while they call state 2 dragging, this could be things like painting with a paintbrush in Photoshop or moving, it's whatever you're doing while physically interacting with the device. And so the important thing to understand here is that various input devices are not equivalent. So the mouse is one that only has two of these states. It has the tracking state and the dragging state, but not really a state 0. It sort of has a state 0 when you clutch, but mostly you only care about the like tracking state and the dragging state. And then you have the much more complicated thing like a touch screen, which is one that you either are not interacting with it at all, it doesn't even know you exist, or you are actively like touching and moving and dragging things. So this is your classic like touch screen on a phone. Yep.
I was a little confused between tracking and dragging. I mean, I feel like tracking, you're moving and it's...
Tracking is just like the system knows where your cursor is, but you're not actively engaged in an interaction. So tracking supports things like hover, for instance, where your typical touchscreen does not. Like there's mostly no way to do like mouse over, XKCD alt text sorts of things on mobile devices. So the real question here is, what does a three-state device look like? So mice are 2-state, they get 1 and 2. Touchscreens are 2-state, they get 0 and 2. I'm willing to bet that there are at least 5 3-state devices in this room. 3-state input devices. I have one. Does anybody else have one? Show me.
My laptop has a stylus. So.
Okay, there you go. So that's a 3-state input. Who else has a 3-state input device? Nobody else going to claim one? If you have a Samsung Note, you have a 3-state input device because you have a stylus and you can hover and do things with the stylus. The S4 or later, you have a 3-state input device because they do finger hover on those. So yeah, there's actually kind of the comeback right now of 3-state devices where you can do out of range hover and interactions. So I think that's fun. Yeah.
Why isn't a touchpad a 3-state device?
Why isn't a touchpad a 3-state input device? Because usually they don't. Well, I could see that actually. Yeah, I guess the MacBook Pro touchpad fundamentally is, at least to the extent that the stylus case is. So yeah, sure, I'll buy that. I guess it doesn't really ever go into the like I'm not here mode, in the sense that like if you mouse over something and then walk away, you continue mousing over it. Whereas in the like stylus mode, you actually stop mousing over it if you remove the stylus from range, but it's close. Anyway, so the punchline of the models of mouse input story is that real mice are much more complicated. Real mice have movement and hover and drag and left click and right click and middle click and double click, and there's all sorts of things going on in these real estate machines. And it's the reason that still, unfortunately, interacting with mobile devices feels a little bit deficient. It's because you don't have quite the same like level of input as you are used to on a mouse. And it's really hard, actually. I mean, for me, for instance, I have a like big, bulky gaming mouse with like 7 bajillion buttons on it. And when I move from that to using my phone, it feels a little tragic because like suddenly I have like 1 button instead of 1,000. So it's still an open question, kind of how you bring rich pointing interactions into the mobile space. So go solve that problem for us. One potential solution to it is multi-touch. And there are a lot of people doing kind of really interesting things with multi-touch. So the canonical multi-touch is like pinch and zoom and rotation and things like that. But there are kind of other more interesting things going on there. So a strength of multi-touch is that it allows lots of direct inputs. It's very direct manipulation-y. It gets you way more degrees of freedom than you would expect to get from just like a cursor and a single input button. You can do kind of wacky virtual input devices where you say, all right, if I do 2 fingers, it means this. And if I do 3 fingers, it means this, like that car touchscreen thing we looked at on last Thursday. And then you have the advantage that like there's no stuff involved. Like it's just fingers on a screen. There's no styluses. There's no other wacky input devices. You've just got fingers. That's good. The challenges are that you kind of lack tactile feedback in multi-touch usually. And the reason for that is that while we can do some haptics on like a soft keyboard where like the phone vibrates a little bit every time you hit a key, what you can't easily do is do haptics for different parts of the device. So if like your left finger is hitting a button and your right finger is not, it's really hard to like haptically signal that. It does require free use of both hands potentially, and usually eyes to look at it. And then you have all sorts of like fat finger problems with precision and occlusion and how do you actually like hit the target that you're trying to hit. So some terms you should know. There's a difference between a touch table and a touch screen. Touch tables are like big surfaces that can detect lots of different touch points, whereas like most touch screens are limited to like 3 to 5. Single finger versus multi-finger gestures and touches. Multi-person versus multi-touch. So it's kind of a different notion of having like 6 people sitting around a table and interacting with it versus having 1 person with 2 points. Points versus postures is really interesting. There's all this research about how you like infer input intention from like the way a person is sitting and how they approach the input device. And then hands and fingers versus objects. So there's lots of research on what if I have like lots of smart devices that I put on a tabletop surface and then want to do innovative interactions with them. So there's that. There's a vocabulary out there for multi-point gestures. I don't expect you to know this, but it's kind of interesting where people have sat down and said, all right, what are all the like multi-touch, multi-point, multiple hands on the table gestures we could plausibly support in a UI? And what interesting things can we do with this that we wouldn't be able to do without it? One more kind of quick thing to address is the fat finger problem and occlusion. So we have this issue that keeps coming up on phones and also on like smartwatches, where if you're trying to do target selection, you can't see what the hell you're trying to press because we don't sadly have clear fingers. That would be a good innovation though. Somebody get to work on that, clear fingers. But barring that, we have to come up with some way to like make this work without being able to really see what you're tapping. And that's kind of sad, so it gets the big red X. Who's got solutions for me? There are various canonical solutions to this problem. Yeah.
A keyboard, for example, when you press the letter H, a larger H hovers above your finger.
Okay, so you can separate the kind of locus of interaction from the locus of attention to some extent and show people elsewhere what they're actually pressing. Yep.
Well, it kind of disconnects the finger from the screen. You can also, because the way a finger is shaped, the first point of contact can also be the location which is pressed.
Yeah, so you can choose selectively amongst the like surface area of the finger to decide what they were trying to hit while they were going in there. Yep.
So this is less like, this is kind of more scientific, but I was seeing there's a company online that has a touch screen that sends electric signals and sends out like little bumps.
Cool.
If you're like
Mhm.
touching the, so.
Disney research was working on one of those for a long time where you could like on a flat surface feel different things on different parts of the surface based on them shocking your fingers in interesting little ways. It was Carnegie Mellon and Disney Research Pittsburgh, which is at Carnegie Mellon. Yep.
You can put an active touch screen on the back of the device.
Okay.
So that it senses where the finger hovers and displays it.
All right. So I've got a slide for that one. So there's all sorts of people out there trying to do kind of interesting things with like active touch on the backs of devices. So here is a multi-touch gesture happening where one hand is on the front of the device and one hand is on the back of the device. And in this particular mock-up, they're doing something interesting to show you like, I guess the screen is either partially transparent or they're projecting somehow your hand. But the idea is that you can do these sorts of like back of the device gestures. Do I want to do Lucid Touch? Sure. So here's Lucid Touch, which is another one of these like back of the device interaction techniques. Very cool. All right, and then I want to show you one quick video of a like postural interface. So a lot of what we've talked about so far has been about like pointing and selecting and very kind of practical task-oriented stuff. I do want to note that a lot of the like interesting work that's going on right now in input devices is on kind of artistic expression in input devices. So here is one posture-based interaction. And so the idea of this thing is that it's all gesture-based, but it still does very different things based on like how the person approaches it. And if you have never seen any of this stuff, just go to YouTube and put in manual input sessions. There's a series of like 20 YouTube videos where they showed kind of wacky interaction techniques. But here's one of them. So the people that make things like that are the people that you want to hang out with at the bars after Kai. So this is a different posture. This is same hands, but just a different way of approaching the device. So anyway, there's a lot of these. Very interesting to check out if you've never seen. So I don't have slides for it, but what is due? Heuristic evaluation due today? Is that going okay? Revisit that. If you did something that was really short and took you like less than 20 minutes, you might revisit the requirements and see if you remember to put in the like introduction sort of stuff. Like I think I've seen a few submissions where people just put lists of heuristics, and I believe there was some requirement for introducing the problem and talking about the context in which the app is working. So check that out. Revisit that if you're worried about your assignment. Contextual inquiry is due on Friday. If you have fears and concerns about your project concept, come and talk to me or come and talk to the GSIs. So I'll be available for half an hour, 45 minutes right after this. And the GSIs have all their office hours. And also, I imagine we'll be happy to talk about these things in section this week because there's not a whole lot else going on in section. So if you have any questions about that, let us know. And then basically, as soon as you get that turned in, it'll be time to start doing your lo-fi prototype. So you have to pretty quickly turn around and start doing like paper and balsamic prototyping. Questions, thoughts, concerns, love, hate, fear? See you Thursday. Huh?
I was kind of confused that they wouldn't, because I don't think there is any part where it comes to do
some context.
Because I was kind of right. So I don't.
If I were you, I would go back and put in like at least a little tiny bit. I mean, it doesn't need to be much. It shouldn't take you very long. But just like give us a little bit of information about what's going on.
Did you manage to think of anything?
Not really. So I mean, I could point you towards dozens and dozens of papers.
I just don't really know what to expect because I've never. I mean, human factors has always struck me as something that is not really well defined for any specific purpose. It's kind of just like human in the loop.